Alright, so work and energy, multiple choice 2, number 13. Number 13, this brings up actually a way of looking at potential energy that we have not this year yet discussed, so it's understandable why this question would come up. See, our current view of potential energy is a bit of a simplified one. See, we spend our lives within a very, 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 very close distance to the Earth. If this is the surface of the Earth, this is actually even smaller, probably. And this is actually too large of a description of our atmosphere, for example. And, you know, truth is, Mount Everest would be like a little hardly noticeable bump on the surface of the Earth. We think we're, you know, hot stuff if we climb to the top of it, but truth is, compared to the size of the Earth, we have not gotten that far from the center of the Earth. So all of our gravitational potential energy needs occur within a very close space. And so we use this simplified version where 0 is the ground level, and the farther away you move, the higher your energy goes. And it works just fine. Because all that really matters, gravitational potential energy, is that your height changes. It's all relative. It all depends on where you want to set 0. Well, when you back away and you don't take such a small, narrow-minded type view, and you look at the Earth in its place in the universe, it's very tiny. And yet its gravity can be felt, theoretically, even far away. But what's interesting is that the farther away you get, you might remember, the force of gravity gets less. Right? Because big G, mass of the planet, in this case the Earth, the mass of you or spaceship or whatever you're moving far away, over the distance away from the center of the Earth squared. And so this force gets less as you go farther away. See, when we're here on Earth, we don't worry about the fact that the force is slightly less on us on the top of Mount Everest than it is down here. It's basically, we just call it the same, our weight is the same. But technically speaking, if you brought a scale to the top of Mount Everest, regardless of the fact that you'd lose weight because you're working hard, blah, blah, blah. If you had the same mass, you would read a different weight. You would be slightly less, you have less weight at the top of Mount Everest because you're just a little farther away from the center of the Earth. Well, but we can ignore that and use this. But here, if you start looking at distances and situations where you're very far away from it, you can't really do that. So, for this larger view of things, what's done is this. They define the potential energy this way. They say that the gravitational potential energy, interestingly enough, negative, big G, mass of whatever planet we're talking about, or sun or whatever, little m would be the mass of whatever object you're moving away from it, or towards it, or whatever it is, divided by the distance. And it turns out to be just the distance. That way the units work out with joules to be joules, and we don't even worry about that, but it's very similar to the one for force. In fact, if you think about it, you multiply by a distance, one of the r's would cancel, at least unit-wise. So what this negative means is no matter where you are in the universe, your potential energy in relation to the planet or the sun is negative. Yeah. So that's fine. Your 0 point is actually some imaginary point infinitely far away. Because if you get really far away, R gets really big, doesn't it? And the bigger this gets, the bigger, you get a big number divided into a smaller one, this approaches 0. So at, quote, infinity, it goes to 0. And the universe is not small. So you can get very, very, very far away from Earth and basically be like, I have no end. I'm not going to be released from here, some point way on the other side of the universe, millions of light years away, and start falling towards Earth. It's just not going to happen. Even though theoretically the Earth is pulling on me, no, it's basically we can say we've gotten to the point where we're at 0. That's why physics is awesome. So this is the way you would look at potential energy when you start looking at it from a big scale picture of this. That's where this equation comes from. I've lost it here. Where'd it go? That's not it. I had it. already did. I just had it. There we go. Okay. So that's where this comes from. You know, we don't really need to know all exactly why, as long as we're willing to accept that this is, hey, for this problem, there's your equation for gravitational potential energy. Fine. What I would suggest for this one, in fact, I would say, see if you can figure it out, like pause the video and see if you can figure it out on your own after this. But this is all about the conservation of mechanical energy. The mechanical energy before it's launched, this object's launched, so it's here on the Earth, on the planet or whatever, and it's launched outward like this, and it's non-rotating, no atmosphere, just because those would confuse the issue a little bit. And with a certain speed, this bizarre thing right here, and they want to know the farthest point of it. In other words, at some point out here, it's going to stop. All right. So the mechanical energy initial occurs here when it's launched. And the mechanical energy final, I would look at, is out here when it stops. And those two have to be the same, because there's no atmosphere to interfere with it. It's just gravity is the only force. So the kinetic energy and the gravitational potential energy and the kinetic energy are just, it's like a roller coaster. They're going to get exchanged. So mechanical energy final. They have to be equal to each other. There's no frictional forces or anything like that. All right. After it's done being launched, it has this velocity. That's it. So I would pause it and see if you can figure it out from here. If not, I'll give you one more thing. In the beginning, it has two forms of it. It has both gravitational and kinetic. Because in the beginning, it is not at the center of Earth. And this equation, this r, this distance, is from the center of the Earth, not from the Earth's surface. So it has a little bit of potential energy due to its distance from the center of the Earth. And it obviously has kinetic energy due to its velocity. So its gravitational potential energy initial plus its initial kinetic energy is equal to its final mechanical energy. Now when it gets out here and it stops, what kind of energy does it have? Well, since it stops, it doesn't have kinetic energy anymore, does it? So it must all be in the form of gravitational potential. I definitely would stop and see if you can figure out from there. Okay, welcome back. We'll see if you got it right. So initially I have negative big G, big M, little m, divided by, now how far away is it at the start? How far away from the center of the planet is it? Well, it's one radius away. It's on the surface. So I'm going to change this to a big R for my initial gravitational potential energy. Kinetic energy, well, this is a bizarre way of writing the velocity, but it's going to come out nicely with the numbers. It's going to be 1/2 little m times the velocity squared times this garbage here squared. I'll write it out. Square root big G big M over 2R, the whole thing squared, equals, all right, what about our final potential energy? Well, that's going to be negative big G big M little m, using this equation, divided by this final distance from the center of the Earth. I'll call it R final. All right. So let's clean up the kinetic energy here. We're squaring a square root, so the square root goes away. This 2r is in the bottom, and so is this 2 from the half. So I really have big G, this is big M here. It's not really clear in my writing, but it is right here. Little m, because that came with the kinetic energy equation, over 4 times big R. That's what this should simplify out to be. Over here I have negative big G, big M, little m over a single r. And over here I have negative big G, big M, little m over r final. All right, let's do this first. big G, big M, little m, gone in every case. We can divide everything by it if you like. So I have negative 1 over r plus 1 over 4r equals 1 over little r final. Wasn't that convenient? Now, what do you got going on over here? Don't flip all these over. That plus sign, you cannot flip these over. You have to combine these two. So let's combine those two. Let's get a common denominator. If we multiply top and bottom here by 4, I'm going to have to come over here to this part right here, but, well, we'll do it right here. So, there we go. So I'm going to multiply top and bottom of this by 4. So I'm going to have negative 4 over 4r plus 1 over 4r equals 1 over little r final. And by the way, this would be, I lost my negative over here. You see that? There's a negative here, and I lost it. I'm going to put it back. Here we go. So negative 4 and a positive 1. That's negative 3 over 4r equals negative 1 over r final. Now, it is perfectly fine, since you have a single fraction and a single fraction, now you can flip them. This plus sign is now gone. You're allowed to do it. So I'm going to get rid of this negative sign, multiply both sides by negative 1, and I'm going to have 4r over 3 equals r final. That should be my answer. My final distance away from the center of the planet is going to be 4/3 r.